Welcome to this video where we're going to introduce the t-distribution and talk about what this is in comparison to what we've done in the past. So let's set this up as follows. All right. This is going to be starting to open up some of the assumptions we've had in the past related to the central limit theorem as we build the blocks that we need to make some statistical inferences about common population parameters. Let's take a look at the central limit theorem here. It says that the z value, x bar minus mu over sigma divided by the square root of n, follows the standard normal distribution as n goes to infinity. So that's a standard normal random variable as n goes to infinity, and it's a pretty good approximation for a large enough value of n. All right. So what does this require here? Well, one of the things that it requires is that you need to know what sigma is. Requires that we know the true value of sigma. We know the population standard deviation. What if we don't? What if we don't know what that is? Right? We start to say, well, we don't know what our population standard deviation is. Well, if we don't know sigma, then I guess the best estimate that maybe we could think of right now would be to use a sample variance or a sample standard deviation. So what if we don't know sigma? Well, we could try using the sample variance S as an estimate. Or that's the sample standard deviation, sorry. S squared would be the sample variance. All right. So then if we look at what is x bar minus mu, and then we replace sigma with a sample variance S over the square root of n, what is this? This is no longer normal. No longer a normal distribution. No longer a normal distribution. So we're going to call it t. Instead of z, we'll call it t. All right. And so what is t here? The random variable t follows a t-distribution. T-distribution with n minus 1 degrees of freedom. N minus 1 degrees of freedom. Okay. And here's what the t-distribution looks like. All right. This does look very similar to a normal distribution in a lot of aspects. And it should, because all we've done is we've replaced the true value of the population standard deviation with an estimate of the population standard deviation. And so there are some things to be aware of here. First, this is in fact symmetric about 0 as it looks. Symmetric about 0. So we have this symmetry aspect, much like the normal distribution, which is nice. As v increases, right? If we take a look at this carefully, this image here carefully, as v increases, the distribution becomes narrower. The distribution becomes narrower, right? As your sample size increases, right, you're essentially what you're using as, if you think about this as a normal random variable with a mean of mu and a standard deviation of s over square root of n, it's not, but if we just think about it that way for a minute, as n gets larger and larger and larger, this piece right here goes closer and closer to 0, right? And so your standard deviation would be less and less and less. It's just one kind of way to sort of make sense of that. But really what's happening here is as v goes to infinity, this does in fact converge to the standard normal distribution. This does converge to the standard normal distribution. All right. So it is like an approximation in some sense of it. As n gets larger and larger, it does converge to a standard normal distribution. But if n is small, it is more spread out. And so we have more probabilities on the outer edges of our distribution. All right. Let's take a look at an example here working with the t-distribution here. So we'll do a few parts. Part A. With 8 degrees of freedom, what is t of 0.025? What is t of 0.025? Okay. Well, one thing to recall from the chi-square distribution is this is the area, this is the value here that would leave 2.5% of the area to the right. So how can we figure this out? Well, sure enough, we can go ahead and take a look at a table for the t-distribution. And that is, where's the t-distribution here? Oh, must have passed it already. Chi-square, and t-distribution. Table A4 gives you values of the t-distribution, and you can see the image on the top right there. T sub alpha, alpha is the percentage area to the right. So we're going to go ahead and use table A4. We need an area to the right of 2.5%. With 8 degrees of freedom, this table is much like the table that we had with the chi-square distribution. V is 8 degrees of freedom, area 0.025 to the right. That is 2.306. Let's do a few of these to get some practice here. What is t of 0.05 for a sample of size 5? All right, t of 0.05 with a sample of size 5. If we have a sample of size 5, then the degrees of freedom is 4, n minus 1. So we need an area of 5% to the right with 4 degrees of freedom. 5% to the right with 4 degrees of freedom. That would be 2.132. All right. Looks good. Let's keep going. Let's try another one here. C. Let's spice it up a little bit. Let's find the probability negative t 0.025 less than t of 0.05. Okay, you might be looking at this and saying, well, I can't look these values up. I don't have degrees of freedom. Well, think about what this means. T of 0.05 is the number, the t-statistic number that you would get that leaves an area of 5% to the right. And negative t of 0.025 leaves an area of, so think about what this would mean. Negative t of 0.025. Because the t distribution is symmetric, if this was just positive t of 0.025, you would leave 2.5% to the right. But because this is negative t of 0.025, this is on the left side of the spectrum. This is going to leave 2.5% to the left. To the left, right? Let's draw a sketch of where these numbers are. Remember, the t-distribution is symmetric, much like the normal distribution was, so we can do a sketch real quick. T of 0.05 is going to leave 5% to the right. So if this number is t of 0.05, then there's 5% of the area over here. If t of 0.025 is like right here, if this is t of 0.025, that would mean that this would be 2.5% area over in this direction, but it's the negative of that number, so we're looking at this number right here. So by symmetry, this is going to be 2.5% of the area. So what's the probability that we're between these values? Well, we're looking for this probability right here. And what have we excluded from this? We've excluded 5% to the left, and we've excluded 2.5% to the, 5% to the right and 2.5% to the left. So we've lost 5% on the right, and we've lost 2.5% on the left. So the total area in between is 92.5%. There's actually no need to look any values up in a table here whatsoever. Let's try one more here, part D. Just trying to get some familiarity with the t-distribution, right? This relies on pulling our skills from the normal distribution where we started using things like symmetry. We want to bring that back into our skill set here. Let's find a value of k so that the probability k less than t less than negative 1.761 is equal to 0.045 for a random sample of size 15. For a random sample of size 15. All right. Well, size 15, that means we have 14 degrees of freedom. 14 degrees of freedom. And let's see what we have here. Well, we want a probability t being between negative 1.761 and greater than k, all right, to equal 0.045. So we need 0.045 equal to, how did we calculate probabilities like this? Well, this is the probability that t is less than negative 1.761 minus the probability that t is less than k, minus the probability that t is less than k. All right. So then I'm going to have to ask, what is the probability that t is less than negative 1.761? Well, can we go look at the table with 14 degrees of freedom? Where is negative 1.761 showing up? Well, that's the normal curve table. This is the t-distribution table. There's no negative values in my entries here. There's no negative values in my entries. But, I do have the probability, I do see a 1.761 with 14 degrees of freedom. 14 degrees of freedom. And that is 5%. 1.761 is right there. You can try to point you in the right direction here. And that is 5%. Okay, well, so that means 1.761 leaves an area of 5% to the right. So we do know that 1.761 leaves an area of 5% to the right. Well, then what would be less than negative 1.761, well, that's just the symmetric part of the curve. That would leave an area of 5.5% to the left, which exactly coincides with being less than. And so that would be 5% minus the probability that t is less than k. And so now we can add some things over to the other side here. I have positive probability that t is less than k is 0.05 minus 0.045. That's 0.005. And so now I need to find the probability that t is less than k is equal to 0.005. Well, let's take a look. Again, how can we figure that out? So here's our curve. So 0.005 is probably going to be some value over here. So this is the k value that I want. I want an area of 0.005. But the t table gives me areas to the right. Areas to the right. So I'm probably going to end up looking for a value over here that's going to have 0.005 area to the right. Under 14 degrees of freedom, what can I find for that? 0.005 with 14 degrees of freedom. And where's 14? 14, there we go. Do we have a 0.005 for the t-distribution? Certainly we do. There's a column on this table, 0.005. 14 degrees of freedom is down here. That is 2.977. 2.977 is this number. This is 2.977. So by symmetry, k has to be negative 2.977. So k is negative 2.977. There we go. All right. And that is just an introductory look at the t-distribution and getting some familiarity, really just working with the table and the notation as well. Okay. I think this is a good point to pause, and I'll save this for a separate video. In the next video, we'll kind of look at the actual application here, right? Because the whole motivating factor here was, what if we don't know what the true value of sigma is? Can we still do some sort of probabilistic questions? And the answer is yes. And in fact, what we can do is, if we know the sample standard deviation, we can start to try to infer on the population mean mu. We will see you in the next video.